Hi everyone. I'm super happy to be here to talk about a topic I'm actually very passionate about, which is big blocks. But to be honest, I was a much bigger fan of bigger blocks back in the days when Bitcoin had the discussions on big blocks. So I was in the big block camp, not in the crack right camp, but I was for the big blocks. And over the years, getting more and more into the depths of the protocol, I would say I turned into a small blocker by now. Still, the title of my talk is I like big blocks and I cannot lie. I will come to that later. You will see why big blocks. But yeah, don't waste any time and get into it. So on the side, you can see the agenda I want to talk about. I'm basically starting with the components, with the variables that make a block big, which is the block size, starting with the block size, and then we have the gas limit, call data, and the blobs. And then I want to quickly go through a practical example, why big blocks might be an issue. And finally, I want to outline two proposals that are currently, one of them is considered for the next hard fork, for Pectra. The other one is, a little more in the future, and was just proposed a few weeks ago. And I want to quickly highlight them here. But from the beginning. So if you look at Etherscan, this is kind of a quite present screenshot I took from Etherscan. We can see that the block size has stellarly increased, and especially at the end of 2023, we saw this big spike in block size, which was mainly caused by rollups and not blob inscriptions, but inscriptions. So people just posting some arbitrary data. Doesn't matter if it's a rollup or some user, but people posted arbitrary data to Ethereum L1, and they used call data for that. Now, with shipping the Dencun hard fork, the block size calmed down. We are currently at a level of 100 kilobytes per block, which is, I would say, quite healthy. But you can already see we were at almost 200K bytes, as you can see here in the chart. Before getting deeper into it, let's quickly summarize what actually contributes to a big block. And first, we have, of course, the gas limit. The more call data you can fit into a block, so you need a lot of, for example, if you increase the gas limit, you can fit more call data into your block, which then also increases the block size. Second, the call data cost itself. The cheaper the call data, the more call data you can put within your gas limit, which also contributes to a bigger block. And finally, since 4844, we have blobs, and blobs also contribute to bigger blocks. I assume here now that blobs are part of the block, which is technically not true, but still, if you look at it from a networking perspective, I just count the blobs here into the block size. But yeah, forgive me for that inaccuracy. This is kind of the same, but in a little bit more visual representation. You can see before we did 4844, the two main contributors to big blocks were basically the gas limit and cheap call data. So both of them on 2 axes. And then we have 4844, which kind of added 6 blocks on maximum to the current block size. And finally, on the right-hand side, this is what I will talk about a little later in my talk, which is basically an idea of shrinking down the EL side in order to make room for more blobs. But this is then part of the proposals section. Let's first look at the history of the gas limit. You can see this chart shows you the gas used per day, so kind of the summed up gas per day from the beginning since Ethereum launched until quite recently. And the important part in this chart is this section. So this is kind of everything that happened after the London hard fork. So the London hard fork introduced EIP 1559, which kind of created this very nice level, very stable level of daily gas limit used. And if you look closely, you can see that at some point it got very stable. And this is when the merge happened, because with the merge we got a constant slot time of 12 seconds, which meant that the gas used per day stabilized basically at the target, which is super nice to see because it basically also shows us how nice EIP 1559 worked together with the merge and with a constant slot time. Right, this is basically everything I already said. The last point is maybe a little also important. I want to outline that that the gas limit is not controlled by anyone except the users or the node runner, the people running nodes. So the gas limit is raised by the nodes together. So basically, every time we raise the gas limit, it's not like we do a hard fork and just raise it. It's basically the users deciding we raise the gas limit together. And there's currently a community effort. You can find it at pumpthegas.org, where you can basically opt in to signal that you want to increase the gas limit. I'm not for increasing the gas limit, but yeah, I think it's super cool to see the community coming together and coordinating such a change. The gas limit also affects the maximum possible block size of today. What you can see in this chart is on the y-axis, the size of a compressed beacon block. So compressed with snappy compression, which is kind of the standard nowadays in Ethereum. On the x-axis, you can see different gas limits. And what we can see here is today, by just simply calculating the compressed size by using the gas limit divided by the non-zero bytes, the cost of the non-zero bytes gives you the current maximum possible block size. This is still simplified, we'll come to that later, but when we talk about block size, so this is very important here, when we talk about block size, there are different block sizes. First, we can talk about the compressed block size, which is maxed by taking the gas limit divided by the non-zero bytes. Non-zero bytes because snappy compression is very bad at compressing random non-zero bytes. Without snappy compression, the maximum block size is actually above 7 megabytes because you can just take the gas limit divided by the gas cost for 0 bytes, which is 4 at the moment. So if you do 30 million divided by 4, you arrive at the block size of over 7 megabytes, which can be compressed, I think, to around 0.5 megabytes, even lower. So this is not a big problem because snappy compression is very good at compressing a sequence of zeros. And finally, a third size within the protocol is within the engine API, which uses JSON format, and there you basically have to 2x the block size that you already have just because of some inefficiency of JSON. So talking about the block size, we always have to be very clear which block size we are actually talking about. Is it the snappy compression block size? Is it the block size without snappy compression? Or is it the block size within the engine API that then again doubles? Next, we have call data. Call data is currently also, I would say, a widely discussed topic, especially there is an EAP for increasing the call data cost. And currently, the call data cost per non-zero byte is at 16. And you can see on this chart here, if we would go lower, for example, if we would go from 16 gas per non-zero call data byte to, for example, 8, then we would essentially double the block size. And on the other side, the same applies. When we look at the evolution of call data, we can see that it was steadily increasing, but then with more and more rollups posting their data down to L1 using call data, we see this massive spike here, which was also in part, there were also some inscriptions, I think, that also caused this massive spike that you can see here in the chart. And what it shows us, there was a big demand for posting data to L1. Now, with having blobs, this demand calmed down a bit. We saw still some inscription spamming, but not at the levels that were present, as you can see here in the chart. Finally, the last variable that contributes to the block size are blobs. And what you can see on this chart is the beacon block in yellow, which is, as said, at around 100 kilobyte. This is the current average block size. And with 4844, we added a maximum of 6 blobs and a target of 3 blobs. So on average, we will see a picture like this, where you have an average size block of 100 kilobytes, and then you have to add 3 times 128 kilobytes in addition. So what this tells us is, with 4844, we essentially 4x'd the block size, because it was around 128 kilobytes, and now it's at 500 kilobytes. So even though of course, it's on the roadmap and it's great for scaling, but we should not forget that this came with the quote-unquote cost of increasing the whole test. It works. Yeah, as said, the target is at 3. The maximum number of blobs per block is at 6. And then you have already 6 times 128, which means you would have 7x'd the average block size that we had before for 844. And if you visualize that, it looks like this. We saw before we did 4844, it was we only had a block containing the CL part and the EL part, and with 4844 there were these additional blobs. And you can already see at the end of this chart, which still captures this blob inscription spamming we had, you can already see that it's basically the blobs that are responsible for the main load there, or for the main contributors to big blocks nowadays. The thing about blobs is it's actually quite nice because they're of static size. So if we add a new block, we know it's exactly 128 kilobytes. This is not the case for the EL and the CL part of the block. While the CL part is actually quite small, the EL part has a high variance. And you can see that here. This is an average block that you see on the mainnet today, where the CL part is only 20% of the total, and the EL part is around 80%. The problem is, if you look at the max blocks, so the biggest blocks that we see today, then this looks like this. This means 99% of the big blocks is caused by the very big EL part, and the CL part is basically 1% of the whole block. This means there is much room in the EL part and not that much room in the CL part. So this is the question, right? Are blocks too big? And I would like to please raise your hands. Who thinks blocks are already too big? No one? Yeah? Yeah? So can I then assume that everyone else thinks like, okay, blobs are not big and we still have some room? Yeah? Okay, let's look into this chart. So this is basically just comparing reorg blocks with non-reorg blocks. And what you can see here, although we can see that the size, the compressed size, so I'm now already talking about snappy compressed blocks, is higher for reorg blocks than for not reorg blocks, which might point to big blocks having a higher probability of being reorged out. We can already see that at the builders, certain builders, they limit transactions, so you can try to send a transaction that is over 100 kilobytes, send it to all those famous builders. You might have hard times getting that transaction in because the builder is of course concerned that your transaction that is so big might cause a slower propagation, which could mean the builder might lose all its arbitrage opportunities, all its sandwiches that he had in that block just by including your big transaction. So if you want to get such a big transaction on chain, then you better pay the builder well, because otherwise the builder will just discriminate and censor you. The thing is, there's still so much room until we actually reach the max block size. And this is visualized in this chart here. We can see at the very bottom, this is where we are today, the average block, which contains this small line of EL and CL part. We can almost not, and also the blob part is very small, but we could max it out until 3.5 megabyte. And 3.5 is the current maximum block size within, including blobs, so we cannot go higher. But this is, you can see this big gap between the average and the max, and you can already tell, right, this doesn't look very efficient. There is also this line about ERP 7623, but we can ignore that now. I will come to that later. Next, I want to show you this conversation I had with Perry from the DevOps team to come to my practical example that I wanted to present. You don't have to read everything, but it's basically standard, just a very standard conversation between me and Perry, So I'm reaching out to Perry. Hey, Perry, I want to build a big block. Can you help me? He's like, yeah, let's do it. I send him over the block, and you can see on the lower right side, I just put a signed transaction into a text file and sent it over to Perry. And you can already see the text file got quite big, right? So this is how it started, and what I tried to do was basically experimenting, right? I was like, okay, why not experimenting on Sepolia? It's a test network. What can go wrong? Yeah, something went wrong. And what happened, this is 1 month later. So basically at the same day, we submitted that block. We tried to use a GEF node. So we tried to submit my transaction, and Perry was like, yeah, something strange happened. We couldn't submit your transaction. Then we reached out to Justin from Beso, and Justin was like, receiving this file, and he responded something like, okay, nice transaction.txt, that's not suspicious, I will submit it. So Justin got it into a block, and my transaction was basically propagating through the whole network. At some point, I think it was then in the evening already, there was some Twitter user that was like, okay, I'm running a Sepolia node and I get some strange errors there. The DevOps team also looked into that, and basically there was a huge chaos on the Sepolia network. And what happened is summarized in this graph that Marius from the GEF team created. What happened is my transaction got included into a block of the Beso client. The block was then proposed. It was a valid block. It was within the 30 million gas. It didn't do anything wrong. But within the GEF engine API, there was a hard-coded limit of a block size. And this limit declined my block. Declined that block and reorged it out again. The problem was my transaction was paying very well. So all clients except GEF continuously tried to include my transaction, and GEF reorged it out again. And this caused some chaos on Sepolia, and it would have also been possible on mainnet. And this was kind of the very scary thing, because it's basically a very low-cost attack on the network that would mean that every time a minority client proposes a block, it would immediately be reorged out by the majority, by GEF nodes, which would mean that the small clients would be punished by a bug that, that sits inside the majority client GEF. Right, and what I actually tried to experiment with was snappy compression. So I looked into how snappy compression works, and basically, until that point, I think most of the people assumed that the max size block is calculated by simply taking the gas limit and dividing it by the call data cost of non-zero bytes. Again, non-zero bytes just because they can be compressed not that well, and 0 bytes are much better to compress. The thing is, it actually looks like this. If you want to build a max size block, then you should reserve 71% of the gas for non-zero bytes, and then add 29% of the gas for 0 bytes. And this then gives you kind of this line where you can see that at exactly 29% 0 bytes, you can max out the bytes you can include into a block, while still making sure that snappy compression fails to compress. And this is just because of some very suboptimal compression that snappy compression does. And finally, let me quickly talk about some proposals that want to limit the max possible block size of today in order to make some room for increasing either the gas limit or adding more blobs to the network. First, EAP 7623, currently considered for inclusion for Pectra. EAP 7623, called increased call data cost, introduces this floor price for call data. It looks like this. And it basically, very simplified, it does the following. 99% of the transactions use the EVM nowadays, right? So all the pure data availability transactions, they moved towards using blobs. And only 1% of the transactions are still call data transaction, quote unquote. So they would be not affected, 99% of the transactions. All those transactions that still use the EVM would kind of be in the upper part of, or in the first side of this max condition formula. and only 1% of the transactions that are still relying on Ethereum layer 1 for data availability would be in the second part, in the lower part in this chart, and it would that mean that they would pay not 416, so 4 gas and 16 gas for their call data, but they would then pay they would then be 10 and 40. So we would just increase the call data cost for those transactions that rely on data availability and cannot move to blobs. Yeah, as said, it would reduce the maximum possible block size, which is super nice. So we diffuse this DOS vector. 99% of the transactions are unaffected, and it's basically only the data availability users that are impacted by this. And they can move towards block for most of the times anyway. Finally, a very new EAP proposed by Vitalik a few days ago, 7706, which proposes to do multi-dimensional resource pricing, just as we do with blobs already. Vitalik proposed to move even further and do multi-dimensional gas pricing for call data. The goal is, again, prevent big blocks. The problem is, or it's not really a problem, but the challenge is here, it's a little more complex than just increasing the call data cost. So it requires a new transaction type, which means we need to make sure that it's backwards compatible. We already saw with 1559 how hard it is for wallets to implement new transaction types, which might be the same here. So this ERP is definitely, I would say, much closer to the endgame solution than 7623, but it just requires some additional analysis. Right. This is basically everything. I've just put some link here, so you can see there's a lot of analysis on big blocks on ETH Research. If you Google for 7623, if you just look for 7623, which is the EAP number on ETH Research, maybe you add EAP 7623, I'm actually not sure, but then you should find all the analysis done so far on the topic. And yeah, that's basically it. Thank you.
Thank you, Anton. Any questions? Please, Lyle.
Thanks for the talk. So if builders are excluding transactions because they are big, isn't that clear evidence that call data is mispriced? And if your answer is yes, then do you think that with 7623 they would be able to drop such rules?
That's a good question. I would definitely agree that call data is mispriced. I would say call data is too cheap. So last time the last ERP I'm actually not sure when it happened. It's definitely before, or probably 2 years, 3 years, 4 years ago, maybe even more years ago, when call data was decreased to the prices we have today to 416. And builders are, if you would now increase the call data cost, of course, then we would create more incentives for builder to again include those transactions. I think the question is then more, how much would you have to pay then in priority fees? Because the builder is just afraid to lose all the arbitrage opportunities, which he cannot revert anymore. So for example, there are builders doing centralized exchange, decentralized exchange arbitrage. So for the builder, it would be very bad if the centralized exchange arbitrage transaction works and it goes through, but then suddenly his block is reorged where the other side of the arbitrage sits in. So builders would kind of never have a real incentive to include those big transactions, only if you really outpay their arbitrage profits, I think. What was the second part of the question? If 7623 can help there. I think 7623 makes it just less dangerous. So I would say 7623 just makes sure that we will not see those 3.5 megabyte blocks. I would say those really maximum size blocks, they have no real use case except for being used as a DOS attack. Just as an example, for example, Starknet, they are still posting data down to L1 using call data because they use that call data within the EVM. So they need to do start verification, and their transactions are around 90 kilobytes, a maximum of 100 kilobytes. And this might be also a reason, because it might be also based on considerations of builders not including their even bigger transactions.
Any other questions?
You had this nice graph that compared the two block sizes with reorg probabilities, or the other way around. Do you know to which extent this is, or the reorg is caused by just propagation, because, or longer propagation because longer bigger size, compared to like execution, that the execution takes longer?
Yeah, this is a super good question. No, I don't know. Maybe bigger blocks just contain more computation, right? That would be the argument. And then if it contains more computation, it also takes longer. But I think there is definitely a relation between big blocks and a higher probability of getting reorged. And the thing is, those big blocks, they always have cascading effects. For example, if I'm a validator and I receive a very big block from the builder, I just sign the header, and then the block is propagated, then the block takes longer to be downloaded by all the other attesters and then attest to it. The next thing is, let's say my block is not reorged and my block makes it on chain. Then the next proposer might have a harder time deciding, should I build on top of my block, or should I try to reorg that block out? Right? Because also this proposer saw that block later. This proposer also saw this block only received, let's say, 50% of the attestations and is not very strong. And then it's not only the validator that proposed the big block, but also the next proposer might have some troubles. And this is then this cascading effect that we can see in the network. If one block is reorged out, then the next block might also struggle in determining which is the right block to build on top of. But coming back to the question, I agree. So this chart doesn't make it very clear or doesn't reason very well about the fundamental, the very underlying problem there. It's just a comparison where one can quite nice see that those blocks that were eventually reorged out are also on average, I would say, quite significantly bigger.
So if a builder excludes a transaction that's big, why are they included blob transactions today if they are so cheap and so expensive in terms of size?
Yeah, that's a super good question. And it's actually, if you look at the builders of today, so I'm actually currently writing some analysis on that, and builders are already discriminating blobs. Not every builder. Some builders are just applying to the rules. But there is a builder, I will not call him out now, but one of the very big builders, you just have to look at the stats, is including less blocks than so the largest builder includes less blocks than the second largest builder, which shouldn't be the case on average. So builders are already pointing at each other like, oh, have you seen this builder does include so less blocks? Is he maybe playing with propagation time, with latency? And that, I think it's a big problem that is already happening today. Builders not including blobs because they don't make money from them, and it only increases their risk of their own nice, juicy block being reorged out.
We need a .pix to the rescue.
Right, yeah.
Thank you for the amazing presentation.